Now let's take another look at an example of a theorem which is the interior and exterior product with the Hodge element. And so if we let omega be a grade M element, then the regressive product of omega and the Hodge complement of omega all times the pseudoscalar I is equal to the exterior product of omega and the Hodge complement of omega. This is kind of a fundamental observation that's important and that you find maybe in some way or form in some places. And this is a expression of it in terms of the operations that we're using the foundations of differential geometric algebra. And we're going to attempt to provide a proof of that here by expressing it in this way. So based on the properties that and the expression rewriting that we've done, we can rewrite the expression in this way such that we end up with a exterior product expression instead of a regressive product. And then we can factor out the metric tensor component from the Hodge complement component in such a way that we can apply the complement of a complement axiom restricted to the original Grassmann complement to the expression and rewrite the expression in such a way that we have -1 times m to the n minus m. And then we have the exterior product properties that we can apply and rewrite the expression once again, and we can have a simpler exterior product expression as that we can now refactor actually again the metric tensor component that we factored out into the exterior product expression that we have in order to make the Grassmann complement into a Hodge complement, because this extra factor is basically what is the difference between those. And then we just note that we have to multiply this whole expression by I, the pseudoscalar, in order to prove the theorem. And so that's how we can get theorems like this that we can observe using differential geometric algebra when we explore the properties of the elements and the algebraic expressions that we can make. So we've seen that we can construct expressions using the Grassmann and Hodge duality complement and the exterior product and the regressive product, and we can create expressions that are equivalent to each other and make proofs of that. Now, another thing that we can do is we can extend this proposition of writing variants of expressions by making variants of expressions that involve the interior product and the exterior product. So suppose now, what if we want to write the exterior product not just in terms of a regressive product, but an interior product? And this is what this theorem states, that you can do this, and you can also write an interior product in terms of a regressive product, which can be written in terms of an exterior product. And so this is kind of another variation on extending beyond what we just did in the previous theorem, which goes to show that we can find interesting formulas relating expressions with exterior products, regressive products, interior products, and the Grassmann-Hodge complements. And if we move on to the next theorem, actually, here's another more simple result that we could consider, that if we have eta and omega being grade m elements, then if we take the reverse of those elements, the inner product still equals the other interior product. And that's due to the property of squaring the powers of -1, which just cancels out those, making the expressions equal to them. Having taken a look at some of the variants of expressions involving interior products, we can now take a look at this corollary involving the absolute value of an element omega squared, or the interior product of omega with itself. So if we take that and multiply it times the pseudoscalar, that equals an exterior product expression based on the theorems that we've been taking a look at. We can see that that's a result basically by applying the last few theorems. And then because we've now rewritten the interior product as the exterior product, and we can actually go a bit further and not just rewrite this as an exterior product, but we can make it a geometric product. And rewriting this as a geometric product, we have the Hodge complement still in our expression, but even that can be rewritten as a geometric product. So we rewrite the geometric product once more, and we obtain the reverse of omega times I, the pseudoscalar, and that turns out to be just the absolute value of omega squared times I. And this is basically if and only if we choose basically that the interior product of omega with itself equals the reverse of omega times omega using the geometric product. And this is basically one of the reasons why we have chosen some of the definitions we've chosen in terms of the original Grassmann algebra foundation. Is we want to have this arrive at this corollary, which helps make sure that we're using the correct algebraic properties. It's now time to address a divide in the geometric algebra literature. Specifically, if you've done enough studying about geometric algebra and Grassmann algebra, you will know that there are both a left and a right contraction which can define the variance of the interior product. Now, in this presentation, I've tried to avoid up until now addressing which one of these I've used, because I want to address it now at this point where we have enough foundations to talk about this. But up until now, I've just been using the right contraction, the original Grassmann right contraction as the default interior product for what we're talking about. And this is true to what the original Grassmann algebra did and what John Brown was talking about in his exposition about Grassmann algebra. What actually is the difference between the left and the right contraction? Well, if we take a look at the table we have here, this table which I created demonstrates that when we look at the geometric product construction of the left and the right contraction, where it's the reverse of eta times omega using the geometric product, and then using a grade projection using s minus r or r minus s to project onto the grade space. So what was the actual difference there between the left and the right contraction? It was s minus r and r minus s. And due to the way grade projection works, you can't have negative, grades. So the operation actually just is 0 when it's negative. And so that is the difference between these two operations, is how the grade projection behaves based on the parameter s minus r or r minus s, which is determined by the grade of the input elements eta and omega, r and s. If we look at the other side of the expressions in the table, we see that we can use a regressive product in the Hodge complement to express the same contraction product instead of using a geometric product with a grade projection. So by just applying the grade projection on the inputs omega and eta, we can restrict ourselves to the S and R grade, and then we can use the regressive product in the Hodge complement in this compositional way, such that it gives us the same result as when we use the geometric product and the grade projection. But what is fundamentally important here, which differentiates some of these expressions, is the role of the reverse anti-automorphism in the expression. So in the geometric product expression we use a reverse anti-automorphism, whereas in the regressive product expression we don't require it. This is where I've discovered a multiverse of variants of interior products, which is a rift in the geometric algebra literature. And this table here maps out what I've discovered out in the wild world of, in the wild west of geometric algebra, where there are different types of expressions out there. And in particular, the way this table works is it's actually quite systematic, and it's fully kind of maps out most of what we would see in terms of variants of these. And the most important one really is just the Grassmann and the conventional variants. Now the Grassmann one is what we've been talking about in this presentation so far. It's just the first row in that table. And now what happens if we just focus on the right-hand side of the expressions? We see how the geometric product is a composition of two elements, eta and omega, and one of them can have an anti-automorphism applied to it, which is the reverse tilde operation, and the other one doesn't. And you can swap around which of the input arguments has the anti-automorphism applied to it, or it could be neither of them or both of them. Now the Grassmann original definition would involve a single anti-automorphism on the left hand argument, while the conventional approach has no anti-automorphism in the geometric product expression for the contraction. Instead of using the geometric product expression on the right hand side of the formula, we can also take a look at the regressive product expression and how the anti-automorphism is applied to the input arguments and how they compare across the table. And similarly, we can find that there's a pattern which is similar but not exactly the same pattern as with the geometric product expressions. Alright, so why would I bother tabulating this multiverse of possible expressions for the interior product contraction, which has a left and a right variant and a Grassmann variant and a conventional variant? Well, the reason why this is tabulated here is because as I was reading the geometric algebra literature and differential geometry literature and trying to unify these things in my mind and build a foundational structure that is consistent across all these different things, I realized that some of the literature was using the conventional definitions when referring to things, as opposed to the original Grassmann definitions, which are used in a lot of differential geometry and the original, well, Grassmann definitions. And so some of the newer modern geometric algebra literature, unfortunately, somehow diverges and uses the conventional expressions instead by default and implicitly in certain ways and expressions. And so it's important to understand this fundamental distinction that in some ways the expressions, the result of them, they'll overlap with each other and be the same in a lot of cases, and there'll just be some special cases where the results differ due to how the anti-automorphism application affects a definition. So the important thing which this table tries to emphasize when I created it was that some of the different literature out there will stick to some particular convention implicitly in their definitions, and which are different from the original Grassmann implicit conventions. And so I would like to be able to map that out and understand and differentiate that and be rigorous about the mathematical origins and meanings of these expressions and disambiguate the context of the language in these different contexts. Does this present any practical problems? Well, as if we just stick to the multiverse of the variance of interior products the way it is in this table here, it's not all too bad, because each of these expressions can be obtained from another one by applying some anti-automorphism to the input arguments of these expressions. And so it can all be recovered and we can translate between these things, and it's not that difficult once you're aware of this, just to kind of keep track at the back of your head, whether you need to apply some anti-automorphism when you're understanding different literature out there in terms of what variant of interior product is implicitly assumed in the definitions. Now, there is a particular reason why in the foundations of differential geometric algebra, as I have laid them out and constructed them so far, why I've chosen to use the original Grassmann convention and definitions in my work. It's because there are theorems and definitions which are found in some of the differential geometry literature, and especially in the Hodge and the Ram things that have been written that are based on that. They will use some theorems and definitions which are compatible with the original Grassmann algebra, and some of the other geometric algebra literature, it has some slightly different implicit assumptions about how the anti-automorphisms are applied to the interior product contraction variance, then that is something to be aware of, and it could make some of the results incompatible by having a plus or minus sign end up in an expression being equal in such a way that it makes all of the mathematics inconsistent. So that is something you might have to worry about and be aware of, and that is one of the problems and issues I'm trying to address by having awareness of it with this table. But why is it important for me to have awareness about this issue with this table? Well, if we take it one step further and we consider that in some people's work they use a complement operation which is not exactly equal or the same as the original Grassmann complement operation or the Hodge complement as we discuss it here in this presentation and this foundations of differential geometric algebra. And so if you start changing that and you start changing the convention that you're using for left and right contraction, whether it's the Grassmann one or the conventional one, then that introduces potential errors and variabilities in expressions and results and theorems, that now it's no longer possible to say that some expression that person wrote in this, when they made these other assumptions, that's at all compatible with the differential geometry literature or the original Grassmann algebra theorems that we're interested in. And so that's why in these foundations of differential geometric algebra, which I'm talking about here in this presentation, and which I've built and implemented in computational language with my Grassmann.jl package, and also into the Julia language and also the Wolfram language. The goal with all that is to have a foundation that's built on the correct, rigorous way of thinking in terms of the original Grassmann algebra, and having the awareness about different conventions and using formulas that satisfy the original theorems of the original Grassmann algebra. Because, I've tested some of the other computer programs that other people have made, and when I check whether the Grassmann laws are satisfied with the complement operations and the regressive product and the exterior product, and trying out different ones of these theorems and expressions that should be satisfied, I find that it's not satisfied. And some of these computer programs that other people have written that claim to be about geometric algebra, they don't satisfy the Grassmann laws or some of the theorems that we've discussed here. And so that's why these foundations I'm building, that's why, some people may have thought this is a boring presentation because it's just a bunch of math and some weird theorems and symbolic notation. But I'm actually trying to address some of the foundational questions and issues, and by building a foundation for differential geometric algebra in the way I have, then we can better understand what's going on in the geometric algebra literature. And if you do encounter some kind of weird discrepancies or errors or inconsistencies in the mathematics, it might be because you use some of these other people's literature where it somewhat diverged from the original Grassmann implicit understanding to a different implicit understanding. So as I've stated several times now, the goal here is to consider the foundations of differential geometric algebra. And the reason why we want to try to get this correct is because we want to be able to use some of the theorems from Grassmann algebra and use them with differential geometry and combine them with geometric algebra. And we don't want to have some kind of inconsistent issues, because when you have an inconsistency, that can lead to just garbage mathematics. Like you might just have to throw some of that in the garbage if it's inconsistent. But just because there might be some issues like that, it doesn't necessarily they are. But there could be some that that I've encountered, for example, when I checked some other computer programs. But when you're reading some of the literature, what you can do is you can try to get the gist of what it is the author is trying to get at, because there is something that they're trying to say, and recast it in terms of the foundations of differential geometric algebra, as I've been talking about here. Because that's what I do, at least for myself, is I try to recast the information that I'm receiving about from different sources about the mathematics of differential geometry and geometric algebra, and I try to make sense of it in terms of the theorems and definitions and foundations of differential geometric algebra as I've laid them out here. that's why I'm doing all this, and I decided I'll record this presentation so that other people can have some thoughts about this as well. Consider the situation where someone is selling a cheat sheet that has all this kind of information about formulas and tables of geometric algebra expressions. And suppose this is based on some computer program and some understanding someone has built up based around using some kind of complement definition that isn't quite equal to the original Grassmann or Hodge complement, or they've made some other choice about the convention in the variance of the interior product. It could be then that these tables and cheat sheets that you purchase, that they're going to be inconsistent with some sort of differential geometry literature that assumes that you have some kind of consistent theorems that satisfy the original Grassmann algebra theorems and axioms. So that's why this is something I like to investigate and think about and be aware about in my own research, at least. And unfortunately, there's going to be some people in teaching this who are going to want to create teaching material, but they're not nuanced enough with their definitions and foundations and implementation of what they're doing and talking about, that they don't satisfy the original Grassmann algebra theorems and axioms anymore. And so that's something that can happen with the ongoing development in history. As people try to spread more information, there's going to be some people who try to teach this material, but they weren't rigorous enough in their definitions. And there have been some people who I brought to their attention some details about the variance of the interior products and how the Hodge complement should be defined, and testing out certain expressions that should be satisfied due to the theorems based on the original Grassmann algebra. And they don't satisfy them, and I show the example, and they just don't want to be that rigorous about it when I confront them about it. And they just want to keep doing it their way because they think it's some kind of choice that you can make that makes sense for them from their perspective for whatever reason. Unfortunately, the issue is that if there is some kind of inconsistency that gets introduced with some of the other literature that makes assumptions based on the original Grassmann algebra, which a lot of the differential geometry literature is based on that. For example, the Hodge and the Ram literature and the writings based on that. They're going to require a nuanced understanding of some of the definitions, and you have to be rigorous. And unfortunately, some of the people teaching this material, selling you cheat sheets and so on, those are not nuanced enough to really take into account all these things. And that's why when putting together the foundations of differential geometric algebra, I'm trying to address some of these things, and that's what this presentation is focused about. There's other presentations you can go to get more of an intuition about certain geometrical insights and things like that. Here, I'm mainly talking about the foundations of differential geometric algebra and what to be aware of. Computational language that's consistent, has the right kind of mathematical properties and theorems that satisfied. It's not just computational language that has to be implemented, but it's mathematical theorems and definitions and axioms that have to be satisfied. That it's necessary to look at the mathematical foundations and the theorems and to think about the proofs a little bit. What that leads to is the design of the computational language that I ended up with, and I put into my code repository on GitHub, Grassmann.jl. And I've now written a paper about it and included a bunch of the theorems, and some of the information discussed in this presentation is all included in the paper about the foundations of differential geometric algebra. It's called Grassmann.jl for a reason, because the emphasis in my program is to try to satisfy the original Grassmann laws and help from that derive the correct understanding, making sense of things in the world. And that's why I created this Julia package, Grassmann.jl, which is available on GitHub. And these fundamental mathematical principles, they're universal, so these things have to be understood before they can be transmitted further, and there has to be a little bit of rigor behind it, and that's why we have taken a look at some of the theorems. I'm just trying to provide my perspective of how the foundations should be constructed for foundations of differential geometric algebra, and Grassmann.jl is a particular implementation of that in computational language, which manifests these abstract concepts I talked about in computational language. And using that, I verify my thoughts about it. Please help sponsor and fund this research and development project. There is a need for funding of mathematical research project outside of academia.